Hello, and welcome to the second of my videos about my new app, MBTileMakerViewer app. And today what I'm going to do is show you how to use Google Earth as a visual georeferencer rather than the built-in georeferencer if you're using Mac, or it's your only option if you use Windows or Linux. So we're going to use the same geologic map that we used in the first video. That is the Kelton Pass Quadrangle in northwestern Utah in the Raft River Mountains. And this is the northeast corner of the map right here. And I have a road intersection, a Jeep trail here, and a road here. And I want to use that as my point. What I'm going to do now is reveal to you that I have Google Earth running in my web browser right here on the left-hand side of your screen. And I've already found that particular road intersection, which is this one right here. Now, the first thing I need to tell you is that you'll get the most accurate georeferencing of the map if Google Earth is set to show you decimal degrees and not degrees, minutes, and seconds. And that's because when Google Earth shows degrees, minutes, and seconds, it does not show decimal seconds. And so the referencing point can be off by up to 10 meters or so. So the way to set that, you go to your account, go to settings, and then we scroll down here and where it says latitude, longitude formatting, click that button and choose decimal degrees. It will work if you use degrees, minutes, and seconds, but it will be more accurate because of the way Google Earth records things if you just use decimal degrees. Okay, that's done. All we need to do here is in Google Earth in the web browser, right-click on the point that we want to use for georeferencing and choose Copy Coordinates. Then you go over to MBTileMakerViewer and find the same point on the geologic map. You right-click on that point and choose Paste lat-long coordinates at click. You will only see this option if you have latitude, longitude coordinates on the clipboard. And it has set the point for us, the pixel coordinates, and the latitude and longitude for that point. Let's go do some two others just to complete the georeferencing of this geologic map. We'll come down here to Cedar Springs, and we'll find Cedar Springs over here, which is up in here. And this road intersection in the image is this road intersection in the map. We go to Google Earth. Again, right-click and choose Copy Coordinates. And then over here in MBTile Maker Viewer, we right-click on the same point in the map and go Paste lat-long coordinates. And we've done that. So number 3, we come down here. We're going to use the 10-mile canyon to get our coordinates. And once we zoom in to the area right here, we find the same point on the geologic map, just somewhere in here, right there. Again, finally we right-click here, copy coordinates, and right-click here and go paste lat-long coordinates at click. All right, we have now georeferenced using Google Earth. Now we can warp this image to a spherical Mercator projection by going to Georeference and, oops, warp to spherical Mercator. and it takes a little while. Note that using Google Earth is nearly as easy as using the built-in georeferencer. So Windows and Linux users, that's the way you're going to do georeferencing, and it works great. All right, let's check our georeferencing because we're in the Mac version. We can see the overlaid satellite view, and we can see that the roads are pretty close to it. It's not a perfect georeference, but it's pretty darn close. If I come here, here's Cedar Springs, and you can see that it's pretty much right on the money right there. So, okay, so that's georeferencing using Google Earth. Now I want to come back here and show you another function that you can use. First, I'm going to erase these control points. And because we're going to start over again. And now what I want to do is show you something which is particularly useful if you have a map like this, where this boundary of the map and the top boundary of the map don't have a latitude and longitude because this map has been cropped from a geologic map. We don't know what the latitude and longitude at this corner is. This is where using guidelines comes in. I do have latitude and longitude here, not at the corner, and down here, also not at the corner. But I don't know where that intersection is in the map. Well, I can put in a guideline to help me. To do that, I go to Map, Add Guideline, or Command L, or Control L, and then I draw a guideline from one side to the other. Of course, we're assuming that latitude and longitude lines are straight in this view. And you'll notice that the line has handles because you'll want to zoom in and adjust it to make it perfectly accurate for there and perfectly accurate for here. And we'll put in a guideline for the longitude value, which is up here. So I'll add another guideline. And we're going to have to scroll down and find that in a minute. But first, let's zoom in and get this one right on the money, right there. And scroll down to here. And now we can drag this end of the line so it's right there. Okay, now we know what the uh, where that latitude and longitude intersection point is in the map. And now we can geocode the map. Now, I think this map has a datum of NAD 83 CONUS. It was published in 2009, so that's what I would guess. The map does not say. But what we're going to do here now is geocode it. And to do that, I'll go Command 1. And this point is minus 113.25. And here, because we have odd number of degrees, minutes, and seconds, I'll type 4157 west, up north, excuse me, that's a latitude, and it translates it automatically. All right, we've done that one. Now we can go to find that intersection point. So we'll do point number two, right at that intersection. 113 space 10 space 30. That's west, and 41 space 57 north. And let's do one more down here. We didn't really need the line for here, but this is 4152.30. And so we'll put point number 3 in here. And again, 113 space 10 space 30 west, and 41 41 space 52 space 30 north. And we're all set to georeference. I could put in a fourth point if I want, but for the sake of time, we'll just georeference this now. Command T, and the program does its magic, moving those tens to hundreds of millions of pixels to their right place in the new image. And there it is. So let's check our result. And when we do that, what we see is there's actually a displacement. It's not a very good georeference. You can see this curve in this road is offset to here, and so on. These roads are offset, and so on. The reason for that is because, in fact, the map is not in NAD 83. It was based, even though it was published in 2009, it was based on an older topo map that used an NAD 27 um, datum. So we don't need to reset any of these points. All we do is need to change the datum pop-up here and then warp the map again. And hopefully this time we will have a better warp. Because the program does an affine transformation, which is a linear transformation, if the map has a complicated projection with curved latitude or longitude lines, the warp is not always perfect. But here with NAD 27, we now see that this road is right on the money and so on, rather than having a displacement of almost 60 or 70 degrees before. So we're good to go. And that's a different way of georeferencing using guidelines. Now I'm going to clear the guidelines because I'm going to show you another aspect, and that is how to warp using a file that has a world file. And to do that, I'm going to drop into here the a LiDAR image of the world file. And the first thing it asks is, well, do I want to merge this with the existing one? In this case, the answer is no, because I'm not making a mosaic. And then because it recognizes that this has a world file with me, it needs a little more information. Is it in decimal degrees, UTM, or spherical Mercator? I know because I made this LiDAR image, that it's in UTM coordinates. And when you specify UTM, you have to specify the UTM zone, which is UTM zone 12 here in northern Utah. So once I do that, it has automatically generated control points for me based on the spacing of the pixels and the projection in the world file, and it's given me 12, which is probably overkill. And so now I have two choices for how to how to warp this image. Um, it and you see them here. When I go warp to spherical Mercator, it asks, do I want to use a more accurate method or a faster method? The faster method will use the linear affine transformation. Um, the more accurate method, which I'm going to start here, actually takes 2 to 3 times as long, but it will have an extremely accurate warp. Whereas the affine transformation, particularly with a large map, might at the corners of the map be off by 5 or 10 meters in terms of its warping. So when we do this, we will see the warped image in just a minute. And here you can see the warped image, and you'll notice that it's rotated. These lines aren't exactly north-south. The Reason why it's rotated is because UTM north is not the same as geographic north here. But we come down here, we find some roads to check our georeferencing on here in the image. Let's come down here and we do that. You can see it is exactly spot on the actual roads. It's a if you have a world file, it's a great way to get an accurate warp. So when you do a warp like this, the program has to decide how to pad these spaces where there's no data when you have a UTM coordinate system. And the way that you specify that is to go to Map and set padding color. Now, the default padding color is a white color with 0 opacity, which means that it is transparent. And that's usually what you want. That is the reason why you see the satellite image behind the warped map showing through. And that's because these wedge-shaped areas on the side of the image are transparent pixels. If you want, you can change the padding color to a different color here. You could make it black and opaque. You could make it black or white and opaque and so on. But you have control over how the color that pads it. Now, because we have a transparent color, when I go save as MBTiles, so I will do right here, you'll see that in the parameters, I have a choice of using JPEG or PNG. If I use JPEG, these wedge-shaped areas will become white because JPEGs do not recognize pixel transparency. They do not have alpha channel transparency. So instead, for this case, I'm going to choose PNG here. And level 19 zoom is overkill. So instead of 0.3 meters per pixel, let's dial it back to 17, which will give us just 22,000 tiles rather than for level 19, 351,000 tiles. And that still gives us a resolution of 1.2 meters per pixel, which is pretty close to the resolution of the LiDAR image itself, because it's 1 meter LiDAR. So I hit OK, and it sits here. It does take a while to generate tens of thousands of tiles. And while the program is chunking away here, it actually took a whole lot less than what it predicted. We're basically done. You can see, you can zoom into the maximum zoom level here, and you can see we can see roads and intersections and so on just fine in this view. So using 17 worked well. Although you can't tell in this particular image, when you import this into an app and say you use it as an overlay like you can do in my GMDE suite of programs, it becomes a nice, these pixels, because we save them as PNG, will be transparent. That's it for my second MBTiles video. And in the third one, I'll talk about how to use GDAL with MBTileMakerViewer app.